form mass number.
We're trying to do formula mass?
Yeah.
Okay. So let's start first. I always start with the periodic table because periodic table is pretty much why stoichiometry was. Okay. So we have a symbol. I'll do oxygen here. So we have oxygen here. We have the name oxygen. Up here we have a proton count. Oxygen is 8. Okay. 8 is the number of electrons oxygen. Okay. And then down here is what we call mass, or sorry, atomic mass. The atomic mass of oxygen is 15.9994. We can call this AMU or grams per mole. They mean the same thing. AMU means atomic mass units. So AMU stands for. This is the same thing as grams per mole. If I can't say anything is per something else, this is per 1 mole. Always. Your bottom number, your bottom unit is always of 1, right? So like miles per hour, 60 miles per hour is how many miles I can go in 1 hour? 60 miles per hour. So grams per 1 mole. Okay. So for every 1 mole of oxygen I have 15.99994 grams. Okay. Every atomic mass is specific to the element. You remember doing mass number for isotopes? Mass number is the number of protons plus the number of neutrons. This is the same thing, except we've averaged all of the common isotopes and we've made a number from that. So the mass number, probably the most common mass number of oxygen is probably 16, oxygen 16. And then maybe oxygen 14. And we average those together by how abundant they are in the universe, and we got 15.9994. So there's more 16 than there is 14, then closer to 16. Okay. All the atomic mass means is for every one grouping of something, because a mole is just sort of a volume in an idea, right? So a volume is something per something. So it would be weight per volume. Weight per volume is density, right? Density equals mass over volume, right? Mass is just a weight in our ideas, right? Or space. And then we have obviously volume. Okay. So it's just like density, where I'm taking up a space of something. Okay. The volume of that thing is a mole, right? The space it takes up is my grams. That's my weight. Okay. So in a balanced equation, if I have something like this, 3 moles of O2, right? And then blah, 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 blah. A balanced equation is not just something, right? If I have 2 moles of O2, what's going to happen is, what this is telling me is I have 2, sorry, I shouldn't put mole there because that's not 2 O2 plus, right? That big number out front stands for mole. Moles in a balanced equation are just a ratio. For every 2 moles of oxygen, let's say I have 3 moles of H2. Okay. Probably not going to work out an actual balanced equation because I would make water, right? So if I make water with it, I probably won't get to that balance, but like for a second, right? So for every 2 moles of oxygen, I have 3 moles. There's 3 moles of hydrogen. Okay. H2 is how hydrogen forms when it's by itself. O2 is how oxygen forms when it's by itself. We're not dealing with ions in a balanced equation most of the time. We're dealing with a compound. So because oxygen and hydrogen are diatomic, I'm going to put in 2s. Okay. Same thing with all of your halogens. That's fluorine solution there. And then we have nitrogen, oxygen, and helium or hydrogen. So this is just a ratio. So I can tell you the weight in an experiment of oxygen, right? I can say I have 32.456 grams of oxygen, right? That I put in this much oxygen, okay? And I'm going to ask how much hydrogen do I need for this experiment to complete itself, okay? So all we're doing is we're using our ratio conversion factor. That's all stoichiometry is conversion factors, except I've given you conversion, okay? So if I have grams up top, I have the grams down the bottom, right? Just like conversions, okay? So all I'm doing is canceling stuff out. This has to be grams of O2, okay? I can't go from grams of O2 to, let's say, grams of hydrogen, right? Grams and grams do not have a ratio. They change based on how many moles we have. So we have to go to moles first. The only thing grams of oxygen can go to is moles of oxygen. Okay. So because this is a compound, people will think, or because it's by itself, right, it's a molecule, people will think that I just need 1 mole of oxygen to make up what is called a formula mass. Okay. If I have a mass of compound, say water, right? Formula mass is atomic mass of 2 of hydrogen plus 1 of oxygen of its atomic mass. Okay. Formula mass just means how many moles of each element do I have in a compound, right? This is telling me I have 2 hydrogen. Just like when we did compounds, when we did naming, we still have just 2. That's all that means is I have 2 to equal my 1. So I have 2 moles of hydrogen and I have 1 mole of oxygen in 1 mole of water. Okay. I can still have just 1 mole of a compound, but multiple moles of the elements that make up the compound. Okay. The reason for this is because all of these together will make up 1 mole of my formula mass. Now, just be very simple about it. Hydrogen is like 1 gram per mole. Oxygen is like 16. This will really come out to like something like 18 grams, right? I'm obviously estimating. I don't have a calculator. Okay, so if I have 18 grams in formula mass of water, right? Okay. We're going to do the same thing we did over here to find our formula mass of oxygen. Okay, oxygen is a molecule / a compound, so we still have 2 oxygen, right? Because there are 2 moles of oxygen and every 1 mole of O2. That's the great part. You have 1 mole of compound, but multiple moles of other compound. Okay. So if we have our atomic mass of an element, these elements make up compounds, right? So if I have sodium oxide, chromium trioxide, right? What this means is if I have one of these, right? I'm telling you I have 1 mole of the entire compound. That entire compound is made up of 2 moles of chromium plus 3 moles of oxygen. Does this make sense? Okay. We're just counting it, right? So to get our weight of this compound, what we have to do is we have to multiply whatever this number is by the atomic mass of our element. And you would add them together to make a total. So 2 times 51.9961 plus 3 of option, which we already know is 15.9994. And yes, you use the longest number that you can possibly find. Okay. Every periodic table is going to say something different because we've all estimated to a different value, right? The periodic table on the test is exactly like these, but they're pretty long. Use the entire number. Okay. You estimate all of them. Because this is the value you have to use in an equation eventually. Right? I'm going to erase this over here. Sorry. Yep. It's just a combination of how many moles of each element are in a compound, right? For every 2 moles of chromium, I have 3 moles of oxygen. Okay. This is my formula mass. Formula mass does not change. Okay? It's just like atomic mass, it doesn't change either. It can be estimated to different values, but it's always going to be the same. Okay. So for every, the individual compound. Right? So this is formula mass. So if I told you that I wanted you to take the formula mass and use it, right, to find moles of the compound, right? I don't need a balanced equation. The reason for that is I would have to tell you how many grams I put in, right? How many grams of chromium trioxide I had, right? So let's say I have 87.243 grams of chromium trioxide, right? That's always how any word problem is going to start, is I'm going to give you a number. Whether that be in grams or moles or particles or atoms or grains of sand, I have to give you a number first to start off with, right? So the reason I tell you that you don't need a balanced equation for this is because I am not turning. Let's be specific. I'm not turning my compound into a different compound. Okay. If I was turning my compound into a different compound, right? Like when we did water, oxygen plus hydrogen, to know the number of hydrogen, right? I have to figure out the number of oxygen. Vice versa, right? Here I'm not doing that. All I'm asking you is if I give you grams of a compound change, tell me how many moles are in it. You would have to be formula mass if you have a compound. If you do not have a compound, and I mean you don't have a molecule either, like O2, if you just have oxygen, right? Not in its elemental form, or in its elemental form, not in its molecular form. You just have oxygen by itself. Yes, we just use the atomic mass. We just use that number down there. Okay? So we have this, right? Grams of our compound have to go down below. The reason for that is I have to cancel it out. That is the very basis of any conversion, is just canceling it out. You want to cancel the units, not the numbers. A lot of people get that mixed up. The reason we're canceling units is because we're using them kind of like variables. Okay? Variables have to be on top and bottom to cancel out. Right? So that's what we're doing. So I can switch to a different variable. So I grams of chromium trioxide, and I want to get 2 moles, right? Do I have a straight conversion from grams to moles? One mole is right, is our formula mass. 1 mole of chromium 3 oxide is the formula mass of chromium 3 oxide, which is, yeah. So if I'm not crossed out, right, moles can be crossed out anywhere. I don't have another moles. That means that's where, if it matches what I need to end with, we're done. All you have to do is that. So if something is below, what it really is being divided. If I multiply by 1, that do anything? No, I just get the same number. So I'm not going to do multiply by 1. I'm just going to divide this number by this number. You can also always rewrite it as this. Everything on top is getting multiplied, and everything on bottom is dividing. Is this not the same thing? Yeah. There we go. Everybody probably. What is it? What am I doing? Oh. Okay. Significant figure wise, is this correct? No. How? What number do I look at for significant figures in this way? Only the first one. The reason this is the only one I look at is because this is a conversion factor. This is something that does not change its effect. So same thing when we were doing like kilograms to grams. We didn't count that one either for significant figures. So we're not going to count this one. So how many significant figures should be in our answer? 5. Does my 0 count? No. 0 in front of a non-zero number never counts. Okay. So I have, these are my 5, my zeros do count, right? Because they're in between two non-zero numbers. 0.5, yeah, there's a decimal point, right? 4, 0, 0, moles, 3 outside. Okay. If you do not label with your unit, it is wrong. It will be wrong on the test. I need to check that. You don't do it to people. So this is what we do when we're trying to get from grams to moles of the same compound or same element, right? It's the same thing if we were doing moles to grams, same thing, okay? If we're going to a different order part, but if we're going to a completely different compound, we're going to need a balanced equation. If you see a balanced equation on your test, and it's stoichiometry, you're going to be doing what's called a mole ratio, okay? A mole ratio is just what I talked about earlier. I'll squeeze your testing. Okay. Mole ratio is a theory that's found. If we do the one I did earlier, with oxygen and hydrogen, I create H2O because this is the synthesis equation, right? This would be actually written, you could write it as HOH, but it's still H2O, right? So I have 2 oxygen and 1. I'm going to do 2 over here. That is 4, 2. You can also do doing balancing, but I did that pretty fast. 4 hydrogen, 2 oxygen, 2 oxygen. So I would give you a balanced equation, and I would say, given 3.9421 grams of oxygen, how much hydrogen will I? Okay. If this ratio is not satisfied with this balanced equation, this 1 to 2 ratio, it will not happen. Okay. The element that makes that not happen is called our limiting reactant or limiting reagent. Reagent is not specifically reactant is. Reactant means it's obviously in front of the equation, not the back, right before the arrow. Reagent just means I can use it in experiments. Sometimes that just people out. Right? So how much H2 will I need, right? So I've given you a number of O2, right? And I want to get to H2, right? This is the transferring of compounds that I was talking about. We're always going to start with the number we know, the number I've given you, right? 3.94021 grams of O2, right? Our first step is to think about how do I get rid of grams of O2? Always. Your first step, well, every step before you can figure out the number should be how do I get rid of the unit 4? Okay. I have to put grams of O2 down here to get rid of grams of O2 up here, right? What is the only conversion that I know from grams? Moles. Moles is the only one I know from grams. Moles is our like stepping stone. Okay. I can do grams to moles, moles to particles, particles to moles, moles to grams, right? I can do that back and forth, but moles is our middle name. So I'm always going to go moles first. So moles O2. Okay. I'm not even going to put numbers in yet. I just want to plan out what I'm going to do. Okay. Now I moles of O2. Is that where I'm going to end up? No. Okay. I want to get to grams of H2. I know grams because I just put in grams. If it just says how much do I need, it could be moles or grams. Right? Okay. So I need to get to H2. Can I go from moles of one compound to moles of another? Yes. The only reason I can do that is because of my mole ratio. Right? A balanced equation says this is specifically true in this equation that for every 1 mole of O2, I have 2 moles of H2. Okay. That's not true every time for everything. But in this balanced equation, it is. So for 1 mole of O2, I have 2 moles of H2. And yes, I write MOL instead of MOLE, just because sometimes when I write MOLE, I get a molecule. Okay. And that's honestly just how my professor said it. I put moles of O2 down here because I'm going to cancel it up top. If I have to fix in grams, am I done? No. What goes on bottom? Moles of H2. 2 grams of H2, right? If I'm going from moles to grams, what is my moles always going to be? 1 mole of H2 equals the formula mass of H2. 1 mole of O2 equals the formula mass of O2. If I'm going from moles to grams directly in one step, that means I'm using the atomic mass, right? These guys are compounds. They're not singular atoms or singular elements, right? So I have to do the formula mass, which is oxygen times 2 if I'm doing O2, or hydrogen times 2 if I'm doing H2. Okay. Anyone tell me the formula mass of O2 not rounded? Times 2. Right? Because it's O2. So we have 2 moles of that and 1 mole of molecular oxygen. What did you say? 31. Okay. What about H2? What's our formula mass? All right, so this gets canceled out, right? And if we've got grams of H2, that means we're done stepwise. Our steps are done. This is the formula mass. This is the formula mass. This is the mole ratio. Mole ratios can only happen with balanced equations. Okay. because they are a truth within a balanced equation. They're not a truth in general. Right? So it's always going to be those front numbers. You know how to approach it. My advice, if you don't want to do it all in like all the top is one step and the bottom is one step, what I do is I do first number, multiply, divide, multiply, divide, multiply, divide. You want to use it in parentheses, right? What is my unit? Uh, Molecular hydrogen is the diatomic version of every element. Sig wise is this correct? How many sig should I have? 1, 2, 3, 4, 5, 6. Do you have the count? 1, 2, 3, 4, 5, 6. That one becomes a 4, right? 4, 8, 4, 3. How do you feel about that one? I think stoichiometry is harder than it looks, personally. But it's a lot of steps. The steps are what gets people up. But I always think when I'm doing these steps is how do I get to the next one, right? Because if you memorize this one and then this one and then this one, I don't think it helps you. You have to remember, why am I doing the next step? Why do I need to do any more steps, right? Because some people just keep going, right? So the reason the steps are what they are is one, first question I always ask myself, how do I get rid of the unit 4? Okay. The only reason I can get rid of grins of oxygen if I put grins of oxygen on the bottom. Stop, be bottom. Okay. That got rid of that. Now I need to think to myself, what am I trying to find? Right? I'm trying to find how much hydrogen in grams do I need to complete this equation. So I know that the only way that I can get to hydrogen in this version, right, is if I go to moles. Because moles is something that we can compare because we have a balanced equation. If we had no balanced equation, I would have to tell you what the balanced equation looks like, right? I could not do it without it. Okay? That's where I get the converting to a mole idea, right? Converting to a mole from grams is only one conversion, right? One type of conversion, and that is atomic mass, right? 1 mole of anything equals the atomic / formula mass of that compound / element. Okay. And then I said, how can I get rid of 1 before? Moles of 2. I want to get to moles of hydrogen. Moles of hydrogen, right? So I can go straight to grams of hydrogen. Got rid of it. That's my conversion to atomic mass. Okay. Conversions are not the easiest things to wrap around if you compare it to something else. A lot of times conversions, they kind of look foreign because that's not how we do any number at all ever in life for that, right? We're just dividing and multiplying things, right? All that this sets up is our units, really. And then we get to fill in the rest. Okay? It's not gonna be like usual. Like if I asked you as a kid how many centimeters were in a meter, you just remember there's 100 centimeters in there, right? You wouldn't be automatically doing that division by yourself. Okay. Here, we're literally spelling out for you what division and multiplication needs to be. Okay? To get from one step to the other. Yes. So if we look at our packets, right on top on the front, this is called the mole map. Right? This helps people a lot when you're trying to think of what my next step should be. So like if I'm trying to go from moles of A to mass of A, i.e. the grams of A, then I have to use molar mass. If I'm going from moles of A to moles of B, I have to use the mole ratio. And if I'm going from moles of A to particles of A, I have to use Avogadro's number. Avogadro's number, I believe, is something you have to memorize. Okay, it's just really big. 6.022 times 10 to the 23rd, whatever. And I really do mean whatever. There used to be an extra kind of question about like how many grains of sand were in a bucket. This works. If I tell you the moles of sand or the grams of sand, you can get to number of grains of sand using the mole ratio. So this is usually called atoms, molecules, particles, whatever. It's the weight of an atom in ratio to the whole of an atom. Okay. So this guy, it's not Avogadro, it's Av. Where's his name? Right? Let's look at it. Oh yeah, Avogadro. This is our other direction. One direction is grams, the other direction is particles, atoms, molecules from moles, right? I would write it like this: moles, particles. That's also stoichiometry. How can I get from one to the other? Okay. So if we do an actual shove, that I'm very bad to is okay. Number 2 on molar molecule practice. For number 3, there's like a weird string of numbers. Don't know why. That has nothing to do with the thing. I'll get that removed. Okay, so we do number 1 on molar molecule practice. So this question says how many molecules? So this is what we're looking for. Molecules. How many molecules are present in 4.98 moles of water? I always say start with the number you've been given. This is where your equation starts. Moles of water. H2O. The reason I'm writing this H2O and not water is for fun. It has nothing to do with this one. Okay. So if I have moles of water here, I have moles of water. I have no idea how to do the equation, I start with that, because I know those two things have to cross out to get to my next one. Okay. Thankfully, for us, there's a direct conversion from moles to whatever molecules. And that is for every 1 mole of water I have, 1 mole of anything, I have 6.022 times 2 to the 3rd molecules. This is nothing to do with formula mass. It's just 1 mole of anything equals that. This is the simpler one people usually get. The issue people have with molecules is understanding what they mean when they mean molecules and remembering the number. Okay. When you put this in a calculator, you will put parentheses around anything with a scientific notation. Your calculator will break it up, even the really smart ones. Should be multiplied this way, this one's on top. Could be a particularly large number. So, what did you guys get? 2.9. Yeah. Let me see how you're doing here. Mine's different. You have to do like the upper one. Yep, absolutely. Okay. The reason it's 3.00, not 3.01, is because I know that I need 366, right? For this guy. So I go 1, 2, 3. I look at this one. This one ups that one, which ups that one, which ups that one, right? So it's 3 even. Right? Those stay zeros. If I moved up, I mean 0, right? From 9. So eventually I just keep giving the 1 to this one. And then what is our unit? Molecules. So with this guy, most of the time it is not a 1-stepper. Like I'm not gonna have to go to particles and then stop, right? Most of the time I would give you a I will have you go to particles from there, right? So I'll have you start with grams, right? Or I'll have you dig yourself out from particles to go to grams, only because it's harder than just doing 1 step, right? So it's the same thing as before, right? Top matching bottom, grams of chromium free oxide. Do we all know why this is chromium free oxide? Because chromium, I'm telling you, has a 3+ charge, and oxygen has a 2+ charge, so they switch, right? And chromium is a transition metal, so it gets the Roman numeral. I just like to make sure. A lot of people fall through the cracks when it goes to naming, and I don't like that because it never goes away. Okay, so because I probably wouldn't even give you this formula, I would tell you this. I'd say chromium free oxide. And then people would write CR3O, right? So there's no prefixes because it's not an equation, so people get messed up. That's okay. All right. So no grams has to go down here. If I want to go to molecules, then I take -12. Okay. If I want to go to molecules, right? I cannot go from straight to grams to molecules. I have to hit our middle guy, which is moles. Okay. The moles of chromium. Okay. I don't even want to put the numbers in over. Okay. This one's gone. This one's gone. So now I have moles of chromium free oxide. It's on bottom, has to go on top. So I want to get rid of it. Moles. Okay. Now I go to molecules. Can I go to molecules? Don't double guess yourself. You can. Right? Because 6.022 times 10 to the 23rd molecules equals 1 mole of anything, right? So I can't do my conversion. Okay. Okay. So that gets rid of moles, right? So if our units are canceled out, that means we're done. Always put it as our numbers. Okay. So if I have grams to moles of anything, how many moles do I have? 1, right? That's my rule. 1 mole of anything equals its formula mass. Now, to do our formula mass is a little nasty because you just have a lot of them, right? I have 2 moles of chromium. Chromium is how many? What is it weigh? One. Yeah. Just one of them. Chromium weighs 51.9961. Plus 3 moles of oxygen, right? Like free oxygen. How much does oxygen weigh? That will be kind of bombarded into your memory at a certain point. How much oxygen weighs? Carbon, because it's carbon 12. Carbon is 12.01, usually 12.0111. Nitrogen, not so much, it's 14, almost even. But some of them just get to you. Like I always know hydrogen and chlorine. Chlorine is 35. I don't know. Anyway, so these two, we're just multiplying this, right? Multiply and then add them together. So to put this in your calculator, honestly, what I would do is multiply them inside parentheses and add parentheses together. 2 times 51 for this E plus. I think that's the easiest way. I have lots of students that write down between every step and then erase their calculating or the next step. That's not helping you, I think. Not just speed wise, you don't need to be like the fastest person in the planet. It just, I think it slows them down and you get mistakes. You gotta say that? No. One. That happens all the time, but that happens on it's only movement on. Don't worry about it. It's how you did the thing, it's not good for that. Okay. So 151, this is our grams per mole. Right? This is our formula. So for every 1 mole I have 151.9904 grams. Okay, so let's put in correctly. So molecules, 2 moles. What is our mole number for molecules? 1. Right? If it's for 1 mole. What if my molecule number? It never changes. I have no way to memorize that. I just have it out all this. 6.02 is kind of a weird number. Even though that's up to remember it. 23, huge. I think that's a bronze number. I don't know. I'm trying to okay. Make sure that's always positive. It's not negative. This is negative. Yeah, let me put that closer. Okay. For this one, multiply by. Suzanne, if you have any questions, you can write in the chat. I can see them from here. Sometimes I can't type in right now. Point 5, 4, 6, 9, 1, 8, 2, 1. Unit. I know that. Do the same thing. Okay. So 6, 4, 3.5. This is going to be more what you're going to touch. Probably 1 or 2 of these where you're going from all the way to the other end of the spectrum, right? One end of the spectrum to the other. That you won't do like a 1 step, it'll be multiple steps. This one, and then you'll have a question like this, where you'll start with a balance equation and then you have to do a mole ratio. We really hound on the mole ratios, mostly because you're about to do that for the next couple chapters. Moles matter like for the rest of the time now. You'll be doing this in lab if you've not already done it. You do a lot of other balance things, but you have to make a balance equation based on what you see. So you want to go more over the conversions, or do you want to go to that composition and yield?
I would do for a mole ratio. We only use that when we figure out how many grains we have.
We only use mole ratio when we're going from one element / compound to the other. So if we're switching compounds or elements, that's when we do it. So I said I gave you a data from oxygen, and I wanted you to go to hydrogen. That's the mole ratio. To get from one element / compound to another, you have to use the balance equation and the mole ratio, because we cannot compare grams or molecules. We can only compare moles, because grams and molecules change all the time based on how many moles it has. So I can also ask you the same question or a similar question about the same balance equation, which is if I input this much oxygen, how much water am I going to get out? Okay, you're going to get close to the same number because your mole ratio is the same, but your formula mass is different. You'll get a different number. Like water has a different formula mass.
So then so if you ask me that, I would take 3 grams of the oxygen multiplied by the formula. Is that mole ratio?
You multiply by this one still. So we're trying to get rid of grams for oxygen. You do the mole ratio with water instead of hydrogen. So you take that 2 instead. And then this would be the formula mass of water.
Okay.
Yeah. We can do another one of those, honestly. I think they're pretty important because they're the stepping stone for the next thing, which is still considered stoichiometry, but it's a little higher. I guess up there, it's a little more foreign than this one. This one at least looks like some conversions you've done a little bit just with new informations. But the other ones, like limiting reactants and formula mass percentage and all of that, are a little bit more helpful. So, okay. So let's see what actually gets you that instead of from my brain. Reactant, practice. Okay. All right, from mass to mass practice, number 3 is 2 silver nitrate, okay, plus barium chloride equals 2 silver chloride and gram nitrates. So, okay. How many grams of silver chloride are produced from 5.0 grams of silver nitrate? I don't need to know my other reaction source. Because if I'm given one of any piece of this puzzle, I can convert to the others, right? I convert to my other compounds for my mole ratio, okay? So I don't know how many grams of silver chloride produced, but that is not the number I've been given. The number I've been given is 5.0 silver nitrate, okay? So we're gonna always start with that. 5.0 grams silver nitrate. Okay. What goes on the bottom? Right? Grams silver nitrate, so we can get rid of it. Okay, what goes on top? Moles of silver nitrate, because it has to be our stepping stone. That would be 1 mole, yes. And this would be 4 mole mass. We'll figure that out in a minute. Okay. What's next? What's our bottom? Our bottom. Oh yes, moles of silver nitrate. Sorry. What's on top? What's the compound we want to get to? Silver chloride. So we have to do mole ratio, right? So this has to be mole of silver chloride. And it wants to know the gram, so we're not done, right? What's the top? So what is our formula mass for silver nitrate? Question before you do that. Is nitrate on the periodic table? No, so you have to count the elements individually. Okay? 1 mole of silver, 1 mole of nitrogen, 3 moles of oxygen. Yes, right. Because that doesn't, there's no parentheses, right? So that only goes to the oxygen. Oh, wait, this is the one I actually forgot. This is 3. 169.88. That's what I got from my repair table. It's using. Yeah. What did you get the big one? The long one. 169.873. I'll probably use your repair table that only had 2 decimal places. Get that? Close enough. It actually probably has more to do with the periodic table than it has to do with any of your guys' ability to multiply stuff. We'll use this one as the official one here, just so you get all the right numbers. Right. All right. So our mole ratio. What is our mole ratio? It is a balance things, right? 2 and 2, which is really just right. 2 divided by 2 is okay. So for every 1 mole of silver chloride, what is my formula mass? This is from the one there. Yeah, here's rounded up to that rehab. All right, all of our numbers in place. Let's see again. Yes, yes. So you're still multiplied by, but if I multiply by 1, it's the same thing, right? So I'm just skipping it. That's my most asked question. Sorry. And silver fluoride. And that would be 266. What would you? Okay, so let's talk about that word excess, right?
What does this mean on the product?
Excess means that silver nitrate. Silver nitrate is our limiting reactant. Our excess is whatever is in our limiting reactant, i.e., when we're done with the equation, our limiting reactant will have used up to do the equation and then it will stop. Okay, so our excess is literally excess at the end, right? I don't use all of it to run through my reaction. So when I run out of silver nitrate, the reaction's done. I could add as much barium fluoride as I wanted. It would still not keep going, right? The minute that silver nitrate burns up or whatever it does, it's gone. The reaction stops. I could keep adding barium fluoride in, and it wouldn't keep the reaction going. If I add more silver nitrate, the reaction keeps going. That's what excess means. It's the one that doesn't stop the equation. The reaction. So if I tell you that this is a limiting reactant, well, and this is excess, then our product should just our buttons. So your number, your grams or molecules or moles do not change if your state changes. Like if I gave you the phases of each of these compounds, if I told you barium nitrate is a solid, it doesn't mean that my grams or my moles or my molecules would change. By the way, I have a question about balance. It doesn't impact anything. Phase just impacts what it looks like. That's it. Okay. Because if a reaction happens, we're saying this reaction happens, right? Then whatever this reaction needs to satisfy it for it to happen has happened, right? If this needs to be room temperature, if this needs to be frozen, or if this needs to be heated up, whatever has happened. The basics don't matter when it comes to stoichiometry. Okay. Part B to this question says how much barium fluoride is necessary to react with silver nitrate. So what I want you to do is not start with the number you have and then translate that into moles and then translate that into barium fluoride moles and then transfer that into grams of barium fluoride. We're going to start with the number that we have not done anything with, right? That we have not changed. 5.0 grams is the same as it was before we did any math, right? 5.0 does not come from us, which means it cannot be wrong. So we always start with the number that could not be wrong, the number they gave us. So to find out our B, we're still going to start with 5.0 grams of silver nitrate. And the question it is asking us is, how much barium fluoride is necessary? If I say how much, I don't care if it's grams or moles. I have to be specific if I'm requesting it in one or the other, right? So if I have 5 grams of silver nitrate grams will go down here, which we've already figured out. 169.8. I'm just going to put 88. Okay, is in 1 mole of silver nitrate. And instead of going to silver fluoride, one of our products, we're just going to one of our reactants. It's the same process. Soluble ratio from barium fluoride to silver nitrate. So you'll get here, and then the same thing. The only reason I stopped at moles here is because it says how much. It doesn't say how much in grams. So I'm just going to do it in moles. Barium fluoride. My key at this page puts it in grams, just because I'm not aware. I think this is the transition to limiting reactants. Because this is the idea of limiting reactants. So in almost every equation, there's going to be a limiting reactant and an excess. Limiting reactant is just what stops the reaction from happening when it runs out. So with these guys, number 1, so this is my balanced reaction. Lithium hydroxide plus potassium chloride equals lithium chloride plus potassium hydroxide. Okay. This is balanced. We have one of everything. Okay. And it says the reaction begins with 20 grams of lithium hydroxide. What is the theoretical yield? Okay. I'll tell you how this ties into lithium hydroxide. I want to find out theoretical yield. All that means is I take whatever number they've given me, which always has to be a reactant, and then I convert it to one of the products. That's it. So you can pick what product you like, but we're gonna start with lithium hydroxide, 20 grams. Grams on the bottom, grams of lithium hydroxide. And then of course we have to go to moles. The reason we're doing that is because I have to go to a different compound. I have to go to one of the products. So I want to see how much product can I make. Okay. So moles of lithium hydroxide here. 2 moles of what product do we choose? Yes, correct. When I do yield, I like to do grams. That's just something I do. Most of them will request in grams, so I just does. Okay. So mole of pH on here and grams of pH. Right, does that make sense? I've done the units. Grams to grams, mole, grams. I want any grams. Okay. How many moles do I have per grams of lithium chloride? 1. What is my formula mass for lithium chloride?
0.941.
0. Point.
Or is it 6? I can't remember.
It's okay. 6.941. So 6.941 plus 15.9994 plus 1.00791. Nine nine.
95.
Okay. Our mole ratio, how many moles of KOH do we have? 1. How many moles of lithium hydroxide? 1. How many moles of KOH in grams of KOH? 1. And then our formula mass for KOH. So K is 39.0983. 39.0983 plus 15.9994 plus 1.0079. I need read glasses, so sometimes it doesn't. So I always make sure that. Okay. So what I'm going to get is grams of KOH theoretical. Theoretical means if I put this much into my equation, based on the math of the rules of my equation, I should get out this number at most. Okay. Experiments are done by humans. We normally get a much lesser number. Okay. That happens to do with how healthy are your reactants. If I healthy, I mean, are they up to their full potential? Are they old? Are they dried out? Did you not use enough? Did you use too much liquid? Did you not get to a high enough temperature? Did you get to too high a temperature? Around 46.85. 555. 46.85555. Yeah. Okay. It's fine. You get somewhere?
Yeah.
Okay. All right. So this is theoretical. I've not rounded it yet for a reason. Okay. So if I say the reaction actually produce 6 grams of lithium chloride, this is my actual. Yeah, a lot less, right? Wait, I said chloride. Oh yeah, because that was the product I picked up.
I think
They picked the product for us.
Right.
Yep, they picked the product for us. Sorry. We can't compare it to a different product. They given us the actual of a different product. I thought they were being sold. Okay, this is more chloride. Well, lithium chloride is much easier to find the chlorine vessel. 6.94. YouTube. 3937. Very bad what? grams of lithium chloride. Thank you. Our actual is 6 grams, so still kind of way off. That's okay. All we're gonna do for theoretical is actual over theoretical. Okay, times 100. Because if I have yield percentage just means times 100. So 6 grams over 5.4 over 2 times 17. Around 17. Just because it's not as precise as here as on a test. I would just say the same that you had here. This is 1, but I'm not gonna say it's 20. That's stupid, right? Because I'm not saying 70% when it comes to lab. So I would just say that decimal. So percentage is a unit. The percent sign is a unit. That's it. 70% is our percent yield. Which means we did really bad. It's a we did really bad. You must never have more actual than you do theoretical. That's really weird. Sometimes organic chemistry you make so much stuff because you're not as precise. Usually that's the issue, we're making too much. But actual should be your salt bar. Okay, so how I said this connects to limiting reactants is the only reactant I can use to find our theoretical yield is our limiting reactant. If I use our excess reactant, then I'm gonna get a theoretical reactant that is not accurate because the reaction will stop before my excess runs out. Okay. If I keep going with something that has a lot more of it, like way more than what the reaction will take, we're gonna get a theoretical yield that is probably actually closer to our or not closer, but a lot bigger than our actual yield. We can only use that limiting reactant. So when we do limiting reactant questions to figure out which one is which, usually we'll do a percent yield right after. So I'll tell you to do. Okay. So you will always be given 2 either masses or mole count of compounds of your reactants. So this is number 3 on the way I was just on. This is my balance equation. They ask you to find what is the limiting reactant. Okay. So they've given us 2 numbers: 0.110 moles of iron, and we've been given 0.13 moles of silver. The reason I got put in conversion is because what I'm doing here is I need to convert to my product from each of these separately, and then whatever number is lower is my limiting reactant. Okay. Because my reaction will stop my limiting reactant. With my excess, it'll keep going and make more product, right? Theoretically. So I have iron and sulfur. They've given us 2 different numbers, which they have to give 2 different numbers to do which one is limiting. Okay. And I always set them up like this: 2 separate conversions. Okay. So I have moles of iron, moles of sulfur. And yes, I'm doing both equations at the same time. And that's probably nasty to look at. And then I'm going to do moles of FES because we have to go to moles first. And I'm not going to go to grams because I don't need grams for B. It'll ask you which one, or it'll tell you which one if you need to go to moles for grams. Okay. So this is the mole ratio from the equation. Okay. It's 1 to 1 on mole. So you can pretty much show you're going to win, right? We convert it to iron to sulfide, right? The reason we did iron to sulfide, like we did our product, is it's the only product. But there were 2, they'd either have to tell you or it couldn't matter. You know what I mean? So when we convert to both of them, because I want to see how much product I made, whichever one makes the least is my limiting reactant. Okay. So this is the most theoretically of my yield that I can make. My yield is my product, right? Yield is how much you yield in a year. Yield is my product. So this is theoretical yield. If you take the theoretical yield of the excess, it'll be wrong. This is excess. If I turn that, if this is my theoretical yield, right? And I tell you that my percent yield for this reaction is 89%, very high, right? Very nice number. Okay. How would you try to figure out what the actual yield is? What's my equation for percent yield? Actual over theoretical, 500. Plug in what you know. It's just algebra, right? So we don't have actual, that's what we're trying to find, so that's our variable. So x, or you just put actual, over our theoretical is 0.10, okay, times 100 equals 89%. I'm assuming all of you have gone through algebra. I think that's become a requirement for this course now, to go through algebra. So, what do you think the first thing we should do is? Then we have to do multiplication bracket, right? What I'm gonna do first is get rid of my 100 because I can't do anything with a percentage. A percentage is not a number. Percentage is unit. We want to turn that to a number. So we're gonna divide both by 100. All that's gonna do is get rid of that times 100. So 89% is 0.89. 89%. Okay. Equals x over 0.10. Now we can multiply 0.01, 0.01. Try to get it out of the denominator. So our actual is 0.81 times. Is 0.089. That would be rare. No, because this one's in moles. Theoreticals in moles, so they have to match. Because your units kind of cancel out become a percentage. So they have to match, whether it's meant to moles. I think technically it could be molecules, particles. As long as they match. No, I've never seen a percent yield done molecules. 0.089. That's our actual percent theoretical. If you can work backwards, if you can go from theoretical yield to actual or theoretical yield to or percent yield to theoretical, whatever, that's understandable reactant. Those reactants go hand in hand with theoretical yield and percent yield. If you do not know what your limiting reactant is, they have to tell you. Right? Like if you're not going to figure it out, like if that's not the problem, they have to tell you which one's the limiting reactant, or tell you like this one, where I said I have 20 grams of lithium hydroxide. Use it to find out our theoretical yield. If I give you one of these and I don't talk about limiting reactant, that's our limiting reactant. Is the one we gave you. Lithium hydroxide is limiting reactant. You cannot come up with these numbers on your own. I don't. So don't even have to forget about that. These numbers will have to give to you, whether grams, moles, particles. A lot of mistakes I usually see is usually this ratio is not 1:1, and usually this actually doesn't start with multiple grams. Do not just look at the biggest number and say that's the one that loses. This time it works, but most times it doesn't. So don't look at like if one is 2.98 grams and one is like 13.02 grams. Don't take 2.98 because it's smaller. You have to go all the way through the equation. Oh, number 4. So number 4 is like a psychological thing. If you apply lighter fluid to charcoal and an open grill and ignite it, which reactant will be the limiting reactant? Okay. So if I have lighter fluid and I apply it to charcoal, okay, which one runs out first when I ignite it? The lighter fluid. The lighter fluid is consumed, right? The charcoal can still burn, but it's burning because the lighter fluid has ignited it, right? It's transferred its heat onto the charcoal. So our limiting reactant is the lighter fluid, the one that gets burned up first. Okay, it stops the reaction, the combustion reaction between lighter fluid and oxygen. Okay, the reaction is not with charcoal and lighter fluid, if that makes sense. Lighter fluid is reacting with oxygen, right? So think of it like gas. Lighter fluid is just a gas in liquid form, right? Just like one of like butane, propane, whatever. Lighter fluid. The reaction is not with charcoal. Charcoal just happens to be touching the lighter fluid, right? If I put lighter fluid on top of charcoal and do nothing, will it ignite? No. I have to have oxygen. The entrance of the oxygen comes from fire, right? When I light a match, I have fire, right? That introduces oxygen and that starts the reaction. The lighter fluid is on, it dissipates right to the air. So oxygen is abundant, right? It's not going to run out before lighter fluid does. Okay. I like this question because charcoal is not part of the equation. Though it seems like it, because I'm adding lighter fluid to charcoal, it has nothing to do with it. Combustion equations happen a lot with limiting reactants. So be able to spot the combustion reaction, which is hydrocarbon plus oxygen equals CO2 and water. Okay. Percent composition is the last one on here. Percent composition is not as hard as it looks, but it can take a long time because if we're doing like number 2 on percent composition, I will run through that one because that is my big long one. If all we're doing is combining 2 bits of knowledge that we now have to understand something else. So number 2, which is the percent by mass of carbon, hydrogen, oxygen, respectively, and atoms. Okay, so this is my compound. You see how I say composition by mass? That's percent mass. Composition. The words move around so extent, right? All that means is part over whole. Part of my compound's mass over the whole of my compound's mass times 100, right? It's the thing we just did, actual over theoretical, just different words. So what I have to do first is find my whole, right? I need to find my formula mass. When I said this one was long, it just means it takes a couple. Right? I have 9 moles of oxygen, 9 moles of carbon, sorry, 9. I have 8 moles of hydrogen, and I have 4 moles of oxygen. So I'm just multiplying their atomic mass by how many moles they are, right? Just make formula mass. That gives me a number around 80. What do you guys do math?
1.1385.
So this is grams per mole. So in 1 mole of aspirin, right? 1 mole of aspirin weighs this much. Okay, that's our formula mass. That's our whole, right? Now, what we have to do is we need to figure out each part, how much it weighs, right? So I'm gonna find out each element and how much it weighs. So these are mole numbers, right? These are how many moles are in that. So all I'm gonna do is I'm gonna take 9 moles of carbon. And yes, it's just carbon by itself. It's not C2 or carbon is that, but oxygen is not O2, hydrogen is not H2 because it's not by itself. Okay, it's an element at this point. Mole carbon, 1 mole carbon. And all I'm doing is taking them to grams. So what you did to figure out this, that's your number that you're gonna get out of this equation. Okay. 8.09. And we do that for all of them, 8 moles of hydrogen. Zero 0.63. And then 4 moles of oxygen. Those are our parts, right? We're not done. We haven't made our percentages yet. Okay. All we have to do to make our percentage is put this number over this number times 100. That's mass percent for each element. Okay. So 1.09 over. Anybody know carbon's mass percent? You can write it. Just take the decimal off. Still 60.
Yeah.
I can. Like 5. Oh my God. Thank you very much. Based off never did the packet. So those are wrong. Okay. So does this make sense what mass composition percent is? It's mass of how many moles you have of one thing in a compound over the whole of the compound. That's it.